example 1.35, just like example 1.30 and 1.20, we are not going to walk through the algebra on how to solve this limit. Here, I just want to give us two examples of the situation where we have an indeterminate form, one of which yields a limit, the other of which does not yield a limit. So let's think of the first rational function here. Now, x squared plus 2 divided by x is a nice continuous function, except at 0. But here I want to take the limit as x travels to positive infinity. And if we attempt direct substitution, we end up with infinity plus 2 over infinity, or infinity over infinity. That is an indeterminate form. So the limit may or may not exist. And in fact, if we look at the graph here, what happens as x travels to infinity? Our function grows without bound. So the limit actually is positive infinity. It does not exist. But just because you end up with a indeterminate form, infinity divided by infinity, does not mean that the limit will not exist. Here we have an example in which we have the same indeterminate form. Limit as x travels to infinity of x over x squared plus 2 returns infinity over infinity plus 2, infinity over infinity. So we have the same indeterminate form, but we can see from the graph that the limit as x travels infinitely to the right, it actually does exist. It's well defined. This function decays slowly down to the horizontal asymptote of 0. So the limit of this function as x travels indefinitely to the right is the constant 0. It approaches the y value of 0. So here we have two examples, a infinity divided by infinity indeterminate form that yields no limit. Here we have a function in which direct substitution gives us the indeterminate form, infinity divided by infinity, but the limit does exist.